We need the multibody dynamics between the car and the street. All cases you see today were run on my PC. This took always between 1 and 5 hours. As soon as you get water into your air intake, the engine dies. But also for electric vehicles, this is important because there the critical zones are the charging port, the battery cooling systems, and in general the power systems. Here it looks more like a roadkill, like I hit a deer or a boar. Normally cars are not swimming, cars are just sinking.
Ladies and gentlemen, I'm super excited to host another deep dive session today, again with ShonDynamics. In this technical deep dive, ShonDynamics demonstrates the power of ShonDy and ShonMesh in modeling one of the most challenging multiphysics problems in automotive engineering, a vehicle navigating through a flooded channel, where fluid dynamics meets structural deformation. And with me today is Moritz from ShonDynamics. So I'm super excited to kick this session off with you, and over to you, Moritz.
Okay, thanks, Joseph, for your kind introduction. Yeah, and welcome again, also from my side. Good morning, good afternoon, good evening. For me, it's now good morning. As Joseph already said, today we will focus on car water management, and I call it wading and beyond, because the main focus will be on wading, and at the end we'll look a little bit on beyond. So what is beyond? Before wading, it's little to no water, so more or less puddles. And on the other side of beyond is if you lose contact and start floating. So when we talk about water management, we have two different main approaches. So one holistic approach where we take the whole car into consideration. So the dynamic between a whole car and the fluid. So in this case, wading, puddles, and floating. Or in a more detailed view where we just have to focus on small parts of the car, like the A-pillar overflow, car doors which intake water or something like this. So to say it simply, the holistic view is there we have a real moving car which interacts with the fluid, and in the detailed view, we don't necessarily need a moving car. In today's deep dive, we will mainly focus on the holistic approach, and maybe if we have time in the next months, then we also take the detailed view into consideration in a deep dive. So I said we, so first, maybe who are we? So we are ShonDynamics. We are a relatively new company. We were founded in 2018 in Karlsruhe, and 1 year later, we opened also an office under Shon Cloud in 2019 in Suzhou, China. Together, we are developing different CAE tools, and two of them you will see today. At the moment, we are together around 80 employees, and more than 50% of them are developers distributed between the different projects. Our main field is at the moment mainly electric vehicles. In today's deep dive, we will see ShonMesh, which is our pre-processing tool. There I show only a few minutes how we handle geometries, how is the meshing going, and then we jump directly to ShonDy. So there, let's say, here is the main magic happens. This is our particle CFD tool. For those of you who are already used to particle CFD, our code is based on the moving particle simulations. This is comparable to the SPH method, but we are solving an additional pressure solving step. The next 2 points will be especially important in our case today, because there we have we need the multibody dynamics between the car and the street, and also the coupled dynamics between fluid and solid. Our product, ShonDy, runs on GPU and CPU, and we can use normal desktop and also HPE systems. So all cases you see today were run on my PC. This took always between 1 and let's say 5 hours, the whole cases you see today. So I said a few times now wading. So first, maybe I want to introduce what is wading for those of you who don't know it. In general, you can say it's when a car goes through a water channel at relatively low speed through relatively high water level. The definition of wading capability is the length between the contact point of the tire and the air intake. From this definition, you already see this was and is relatively or is important especially for combustion engines, because as soon as you get water into your air intake, the engine dies, and even if you don't lose the contact to the street, you won't be able to move without an engine. But also for electric vehicles, this is important, because there the critical zones are the charging port, the battery cooling systems, and in general the power systems. For these kind of experiments, you need huge experiments. So you see here now, for example, this is a water channel of around 20 meters. So if you want to do this experiment in real life, it's really cost expensive. With our approach of simulating it, we want to reduce the cost of the real experiments and have in early stages already covered with some simulations. In today's case, or in today's deep dive, we're considering 4 different cases, 2 different water levels of 20 and 30 centimeters, and 2 different velocities of 7 kilometers per hour and 12 kilometers per hour. As a model for the car, we take the driver model, which is provided by the TU Munich. This is mainly provided for aerodynamics simulations to validate your case there, but we also use it for our hydrodynamic cases. And so that you get an idea of how water weighting is, I went outside for you at a rainy weather and took a video of a car going through a rather deep puddle. And you see at the beginning that the car is also not directly stable. It goes to the left. And yeah, even if in this, let's say 5 or 10 centimeter puddle, the car gets a bit of a problem in stability cases. This was my introduction. Let's switch directly now to the program. First to ShonMesh, so we can talk about a little bit of how we handle geometries and prepare them for simulation. Normally you get, let's say, from customers 2 different kinds of geometry files. One is the STL file and one is the step file. As you know, that the step file is not, I don't like it if I get STL files because there you are losing a lot of information. But yeah, sometimes it's not possible to get something else. So you take the STL file and our ShonMesh can also handle, or at least can manipulate a little bit of STL files. So let's import some of the STL files which are provided from the TU Munich. This looks more or less, you get the body of the car, and then you can choose between different underbodies, between different kind of backs of your car. But this is not important now, so just to try out, we import 2 things. So this is the STL file you get from the side of the TU Munich. So you see already it's a really high quality mesh. So normally it's the other way around. You get a coarse mesh and you want a finer mesh. But now we have already the fine mesh, but then we just to show I want to go in the other direction. So let's say we need a little bit, or it's not so it's necessary to have this fine mesh. So I want to have a little bit more of a coarse mesh on the underbody. And this is really easy with ShonMesh. Just choose the mesh. Then we take the default settings now and generate the mesh. This takes a little bit. Then I can have a sip. And here you see already it's much coarser now. You could use it. You could stitch them together and then export to your ShonDy. But as I said, I like the step file better. This is also provided. So if you go to the site of TU Munich, you can download both so the step file and the STL file. And for the step files, you have much more possibilities to manipulate it and it's much more easy to choose different surfaces, to use different patch names for it. So this is much easier. Here you have some problems of the normals. So you would have to switch the normals of it, stitch them together, and this I already prepared. So this is the car you get from the site, and this is what you get if you use ShonMesh for it. Here I decided, because we have a car weighting case, so it's interesting for us, the coverage rate on the lower half of the car and the upper half of the car is not so important. So I chose all the lower parts of the car, and I said I want a more fine mesh there and a coarse mesh on the button. And this is it. So we can see here now that, a coarse mesh in the upper half and a really fine mesh in the lower half. This you have to do also with your tires, and then you can export them and go directly to ShonDy. And this is what I'm doing now. So ShonDy, completely fresh case. I opened it for you already, guys. So this is a complete fresh case. First, we have to switch from lubrication oil to water because we don't want to drive to oil. This would be a little bit not so environmental friendly. And load our geometry files. Here you see our street we want to go through and our car which we have to define now. And first also the fluid, so we won't forget this one. So you see here now our water level of the fluid. This is too high. So as I said, we want to prepare the third case. So this would be a water level of 20 centimeters from this was a misclick. From ShonMesh, we know the bottom half of the floor of our street will are 1 meter below, or 1 meter and 20 millimeters. And therefore, we have to set our water level 20 centimeters above. It's important to set this small ball inside the fluid domain, in the future fluid domain. And then we just have to go a little bit below 20.02. And this is our water level now. We know 20 centimeters, and this is it. So we are finished with our water definition. Next step would be the car definition. This is more or less two main steps. First, the main steps are the collision models, because the car should drive on the road. So, and because it's not on tracks, on predefined tracks, we have to interact the tires with the car. So we need a collision model between the tires and the street. This is also pretty straightforward. We go to each tire, select the tire, and define a collision model. We have two main collision models. One is the direct mesh collision. So if you have really complicated geometries, you could choose the mesh collision. This would slow down the simulation. If you can, like a tire, which is basically a cylinder, I would prefer or would suggest to select a cylinder. And as soon as we switch it to active, we see the collision model. So we see this is a little bit too large, the collision model of the tire. So we have to reduce the radius. And we see now this works. Now we have to do this for all tires. Yes. I will do it quickly. Active. And then we can check the size is always enough, or not too large, not too small. And it's also necessary to have always the same radius, otherwise the car would behave strangely. So this is the collision of the tires. Then we need also the collision of the road. There we have a little bit more complicated geometry, so because we have to go down and then horizontal and then go up. So this is easier to just choose the mesh collision. And so the car can drive on the street. This is now the first part of the car setup. The next setup would be defining the car directly. There we have simply a vehicle module where you can directly throw in every parts you need for the car and define the correct geometries. So here for the chassis, we need our car model. Then we have to choose 4 different tires. So especially if you want to drive in the correct direction, you have to choose the correct tires. So front left first, then front right, rear left and rear right. And as soon as you define the tires, you already get the information what's upwards and, more important, what's forward position of the car. So later, if you define a velocity, you define the correct direction. The next step would be just defining a mass of your car, let's say to the 2 tons, and tire mass. So every tire is now 25 kilograms. Next to the mass is also two other points are really important: the center of mass of your car and the inertia tensor. In real case scenarios, if you're developing a car, you know already these two values, but let's say you don't know it, then we can also auto-detect it and say, because the problem is a little bit that the car, we are defining it as more or less as a whole body. So the density of the car is completely evenly distributed. This wouldn't be in a real car, so it's maybe more to the front and more to the lower side of the car. So this is, as I said, in a real case, you would know your center of mass, and the same is for the inertia tensor, that this value is really important to have to get a physical behavior of your car. But let's say we don't know it yet, or we don't want to talk to the design people. We help our users with an estimator. This is based on a correlation, so you get directly, let's say, a physical relevant inertia tensor. This is important to say that this is in a relative frame and not in an absolute frame. So we define the pitch roll and your inertia tensor, like if you switch back to the presentation. So this is our definition, or this is the general definition of how inertia tensors are defined in cars. So along the axis is the roll inertia part, and then the pitch and the yaw, like this. Okay, so we have we defined our car. We defined now which parts of the geometry belongs to the car. We defined the mass and also the center of mass and also the inertia tensor. And now we have to also define our damper and spring module. It's let's say an abstracted form of a spring damper system. We have an analytical model of a double wishbone system. The small blue strings you see are our springs. If I switch back to the presentation, so this is a simplified version of it, how we define it. So this is our spring length. Then we can define our angle, and then the values for the damping and for the spring strength, or the spring initial spring coefficient. And the values is defined by how stiff you want to have your system, or yeah. So I have to look at my cheat sheet what I choose there. Let's say if in front and the back are the same values. Also, you can define a initial spring deflection. So if the spring is already loaded at the beginning of the simulation, and also the length and the angle. So if you change the angle, the length here, for example, you see that here this blue lines get longer, and if you change the angle, you see that it's a little bit more steeper. Then here you have to define again the radius of the wheels. This is important. So if you say, okay, the car has to go 2 meters per second, is it the correct wheel radius is important to calculate the correct velocity. The velocity of the car is defined here. I have already prepared okay, this will be our velocity profile. At the beginning, we start with no velocity. I always say to our customers, it's more stable if you don't have directly a velocity at the beginning. So first, let's the simulation run for half a second, 1 second, where no moving starts, and then slowly accelerate the car, and then to its final end velocity. So here, from 0 to 1 seconds, nothing happens. Then we slowly, or we accelerate from 1 to 1.5 seconds, then keep the velocity, and then slowly down again. Okay, this is it. This is how we set up a vehicle case or waiting case. the last point, you can decide if your car want to have a rear-wheel drive, a front-wheel drive, or an all-wheel drive. Here we keep it to rear-wheel drive. And the only thing what you have now to decide is for how long your simulation as a physical time should run. So this is the end time 13 seconds. I calculated that in 13 seconds, the whole car will go through the channel. And also the size of your particles. As in the particles, you can compare it to your mesh size in traditional CFD. So also if you use it, then I would already recommend that you use also a refinement study on the particle size. So as in traditional CFD, where you do a mesh study, you should also do a particle radius study. Okay, this is the setup. We could now start the simulation, but as I said, the simulation would take 1 or 2 hours in this setup. We don't have time for it, so I would switch directly to the results, like in a good cooking show. I already prepared something. This is the same case, but with results. I can hide it a little bit. Here you see, I forgot one thing, the post-processing, sorry. Now I have to switch back. This would be the case setup of the car. But if you want to have some monitoring and post-processing opportunities, like if you want to look at the wave behavior inside your channel, maybe you need a line sample inside the channel to keep track of the water level or something like this. This is also really easy in ShonDy to set line sampling. There later you could track your you could track the water level of your car, or if you want to have pressure sensors in front of the car, you could add a point sampling. Here you should define the position of your sampling point, and we made a little helper so you know directly where you should put the sampling point. This is, let's say, this little helper. There we switch back to the mesh view, and here you can choose the mesh positions. This is a little bit small. Make it a little bit higher, larger. Six. And also a second point, and then we get directly the middle of this of these 2 points and get the direct location. We can copy it and paste it to our sampling point, and then we get directly, if we close it, our sampling point here. And then we have to attach it to the car, so later this point will move together with our car. And as a visual helping that it's attached to a body, we can get this small tick to the sampling point. So now we are really finished, and then I can go back to the results. Okay, back to the results. As we can see here now, we have fluid in the channel starting of the simulation, and then we can directly jump in the middle of the simulation. We can hide it. So we see now the bow wave of the introduced by the car. We can choose the velocity profile. As I said before, we are interested in the coverage rate on the car, so we can choose the coverage rate and hide a little bit into the fluid, so we can directly see, okay, where is water is going, where do we have at this specific moment fluid. Often it's more important to have it a little bit over a time, to average it over a time. This is also no problem. To add a temporal statistic filter, there I want to have the average and not the minimum. And over the last 10 time steps, this would be over the last half second. And then we can choose the coverage rate, and now we have it averaged over the last half second. So this is so in general how we or how the post-processing works in ShonDy. I don't want to show you now all detailed, because then it took much longer. So I switched back to the presentation now and show you the results of the different cases. So switching back to the presentation mode. As I said in the setup, the refinement study is important in traditional CFD, and also you wouldn't believe a normal traditional CFD study without a mesh refinement study, and this is the same in particle refinement, particle methods. Here I did some exemplary tests. So on the third case with 1.2 million particles, 1.8 million particles, and 2.3 million particles. And as you see, the target value would be the coverage rate, the average coverage rate. And as you see, between 1.2 million and 2.3 million, there's not a huge difference, but you can see a difference in the results. And between 1.8 and 2.3 million, this difference gets smaller and exemplary. So you should do it like this. So maybe now one more case, maybe 2 million cases, and see how the results behaving and if you get a mesh or particle independent result. So then go to the overviews of our results. As the 20 centimeter cases, as you see, if it's, let's jump a little bit around the videos on it. If you are faster, then the bow wave is much more, let's say, violent. And if you go in a slow speed into the channel, the bow wave is much smaller. You don't have water on the hood of your car, and this is even worse if you look at the 30 centimeter case. There we get much more water over the whole hood. So because the videos are a little bit annoying, we can switch to the to images. There I can show it better. So here it looks more like a roadkill, like I hit a deer or a boar or something like this. And here, if you go slowing down, it's you have still high water level, but not near the air intakes. And so if you go slower, then you can go to much deeper water, or once deeper water than here. Here you have already problems because water is spilled over the whole hut. The water gets inside the grill. It can take into the air intake, and then you get problems. Also, what I said about the pressure sensors in the preparation cases, I had much more pressure sensors put than in the exemplary case. And here you can also compare how in a slow case, much less pressure than in a fast case, and also that in the higher points you get also fluid there and so on. So this is exemplary how post-processing could work in ShonDy. As a last step, we can also compare the bow waves of the car. We go one through 20 centimeters and 30 centimeters. Here we can see also that in shallow waters, if you have lower water levels, the waves get slower. So here with 2 meters per second, the wave is able to run out the car. So it's the other way around. It gets slower, the bow wave. So the wave is not able to run out the car. So it's directly in front of the car. Whereas in a deeper water level, the wave gets faster, and therefore we are able to run out our car. And therefore, even if it's a case where we have higher water level directly in front of the car, the situation gets a little bit better in comparison. Okay, this would be how we would post-process cases of weighting in ShonDy. At the beginning of the simulation, of the deep dive, I said also that we go beyond. So what's beyond is more or less no water or just puddles. I just want to show you a short video of it. This is more or less the same case, so the same channel, but there we had some speed bumps, and between the speed bumps we have small puddles filled with water. And in the videos you see the reactions of the springs, and also the spilling of the water when it goes through when the cars go through the puddles. Here, maybe I have a small anecdote. So you would say that this is not so important, but I think I lost my power steering in such a case. So I went through a not so deep puddle. But after that, I was not able to power steer anymore, and I had to use a lot of strength to go through to around corners. And the next beyond case is the swimming case. So here in this case, the car goes backwards into the water with 1 meter per second. And as soon as it starts swimming, it tries to get out of the water again by spinning the wheels in the other direction at around 70 kilometers per hour, so 22, 21 meters per second. So now it's swimming. You see a lot of waves are formed, and now the car tries to go out of the pool again. And if you go to the middle of the simulation, you see that if you have a lot of waves, it's really difficult to get out of the pool, because the propulsion of the only of the wheels are really weak. And if you are interested in this kind of simulation, we have a whole series of videos on our YouTube channels and also here on LinkedIn. You could have a look there, and where we directly show, okay, how good is the propulsion of the vehicles if you have only rear-wheel drive, front-wheel drive, or both-wheel drive, and how good is the propulsion in a swimming case. So the weak propulsion of the cars you can see also in this small video. I don't read out the subreddit where I have it from, but if you are interested in more of these cases, then you can have a look. So you see the boat is pulling the car backwards, and you have no chance to get out of the back to the beach, and the car is just sinking, and you have no chance to get back. So here also you see the propulsion of the cars as soon as they lose the contact to the beach. It's really weak. Okay, then now I'm at the end of my deep dive, and I'm now here for some questions, if there are some questions. And I will try and happy to answer them.
So what's the deal with simulating floating cars? Why do we even do that?
It was like I jumped over it a little bit, because for us now it's a really, really common question from customers. So it was already 1 or 2 years ago when our CEO came to us to ask if we can do a demo for car swimming. And then we question ourselves, why should we do a demo for car swimming cases? Because normally cars are not swimming, cars are just sinking. A lot of us saw already this kind of let's say documentary, how to escape a sinking car. So you have to wait until the car is filled with water, and then you can open the door again, and blah, blah, blah. And so I thought it's a bit weird that we have to make this kind of demo. But then we saw, okay, there's a real need for it. A lot of customers ask for this kind of simulation, because they want to have at least some floating and swimming capabilities of their cars in scenarios like you have a flooded parking lot or a flooded street, so the cars are able to swim and to get out of the situation. So even next week, I think I'm at a training station on site of one of the largest electronic vehicles manufacturers, where I give a training about this kind of cases. So it will be in general car water management, but also especially about this car swimming cases.
Mm-hmm.
So it's not just a gimmick that we just thought it's funny to simulate.
Yeah, definitely. People also want to know how they can get in touch with you to test ShonDy and ShonMesh.
There you can go directly to our website and ask on. You fill out a small form, then we get an email, and then one of us will contact you, and maybe we can post the link to our website on the channel or on the chat.
Absolutely, Moritz. With that, thank you so much. Right, this video was recorded, so we'll be also posting this again on YouTube and LinkedIn. So if you have any questions, feel free to reach out to Martin Sonntag or Moritz Schenk. And again, thank you very much. I'm looking forward to more nice SPH sessions in the future. And until next time.
Okay. Also, bye from my side.